Hey guys, I'm doing something a little bit different today. We're going to I'm in the corner actually. You could actually see me. I haven't seen you guys in a long time, and I just want to go over the review sheets that we did and make sure that everybody's clear. So I went over energy sheet 2, but here what I'm doing is I'm going to go over the first sheet, the third, and the fourth sheet, and then that should help you for a quiz that we're going to take on Friday. So let's start with energy sheet 1. And if you just look at the first question, which color has the shortest wavelength? Just going to go over here, just kind of point out that as you go to the left on this chart, wavelength decreases, and visible light, remember we broke that down. The shortest wavelength would be on the left. That would be violet. So that is choice A for number 1. So violet, number 1. Okay, number 2, the energy has the longest wavelength. So we're going to go over here. Longest wavelength would just be that way. And that would be radio waves, choice D. And number 3, in which list are the forms arranged in order from longest to shortest? I don't know if you remember, but we did label this side longest. I'm doing my best to write with a computer animated pen. Not going great. Okay, that's the longest. So you got to look for which choice actually goes from left to right, and that would be choice B, radio waves. Oh boy. Radio waves, then infrared, and then ultraviolet in order. Oh, visible light right here as well. Infrared, visible light, ultraviolet. Number 4, they just wanted to compare the wavelength of UV to infrared. UV is here, infrared is here. So UV would be shorter than infrared. So for number 5, for number 4, you would have wavelength of UV. Oh no, I'm sorry. It says compared to the wavelength of UV, infrared is. Infrared's over here, so we're going that way, and infrared is longer. B. Number 5, when electromagnetic energy travels from air into water, the waves get bent. As soon as you see the word bending, immediately bending, refraction. Number 6, what's the basic difference between UV, visible, and infrared? What you should be looking at on this chart, all of these things are different by their, and it's right on the chart, wavelength, which is choice C. Now, this is where I noticed a lot of people actually got confused. Which type of land surface will most likely absorb more? And I don't know if you remember, we talked about how we get dressed in the summer. And in the summer, we like to wear light colors because light colors reflect and dark colors absorb. So immediately I could eliminate for number 7, they're talking about absorbing, I could eliminate the light color choices. So I'm left with 2 dark color choices, A and C. And we also said that rough textures absorb more. So for number 7, you should have gotten A. Number 8, which diagram represents the relative wavelengths of visible light, UV, and infrared. And I told you that would become very important soon when we're working with weather and radiation received from the sun. So basically what we're looking at is this chart again, UV, visible, infrared, and as I travel in that direction, you notice the wavelengths are increasing. So you're going to want the choice for number 8, where UV is the shortest wavelength, visible is next, and then infrared will be the longest. That would be choice A, according to the pictures. Number 9, how does the amount of heat energy reflected by a smooth, dark-colored concrete surface compare with the amount of heat energy reflected by a smooth, light-colored? So look, both of these surfaces are smooth. So the only difference is one is dark color, one is light color. So how does the amount of heat energy reflected by a dark colored surface compare with that of a light colored surface? The dark colored surface will reflect less because it absorbs more. So for number 9, the dark colored surface will reflect less. And number 10, if equal areas are compared, which Earth's surface would normally absorb the least electromagnetic energy from the sun? I think I told you that the surface that would, what does it say, absorb the least. So the best reflector of the sun's energy on Earth is a snow-covered field. So for number 10, this would reflect a lot of energy and absorb very little. Okay, so that was energy sheet 1. Now I want to go over sheet 3. And on sheet 3, again, I superimposed here the electromagnetic spectrum because we're going to use it for these pictures. Number 1 is asking you, they give you this whole explanation, but they want to know, as water falls near location 1 and moves to location 2, I just got to get a clearer picture of that. So location 1 is, I just got to see it on my bigger picture here. Location 1 is here. And location 2, let me just get that pen going, is over here. So notice it's going to be going down a hill. And I don't know if you remember, we said that potential energy is at its highest when you are further above the center of the Earth. So you're higher at location 1. And then as you head to location 2, you're getting closer to the surface of the Earth. So potential energy will go down and kinetic will go up as you go from 1 to 2. So potential energy will decrease. This picture is super important, and what you need to know is what's happening to the energy of the sun. So as it travels from the sun down to the surface of the Earth, those are ray A, and you can see those are short wavelengths. Then that would be, we get the energy from the sun in the form of, I'm going to do my best, UV rays. So the UV rays are coming down, they get absorbed. Right before they hit the Earth, by the way, right about here, we're able to see them. Then they get absorbed by the surface of the Earth and later re-radiated, and you can see the longer wavelengths. I don't know if you remember in my video, I told you guys that right here, right, this part of the electromagnetic spectrum tells you the story of the rays of the sun. So they come down as UV, right? That's A. They get absorbed, but before they get absorbed, we're able to see them. That would be visible light. And then as they get re-irradiated, they're longer wavelengths, right? Increase in wavelengths. And these are, I'm going to put IR for infrared. Okay, so the answer here, energy B, is infrared, choice D. And then here, number 3, they're asking you what is represented by A. Well, I just marked it up over here, right? UV, UV, ultraviolet. And then we're going to turn the page. And I put a picture of a roller coaster here. Look at that person, very, very happy on that roller coaster. Good for them. And they are starting at point A and they're going down. And if you have ever been on a roller coaster, you know how fast this starts to go. So here's the question. At which point is potential energy the greatest? Remember, the higher you are above the surface of the Earth, the more potential energy you have. And look, D is at the top at this point of the roller coaster, but A is by far the highest. So the most potential energy is right here at A. And question 5 says, what happens to potential and kinetic energy as you go from A to D? So I'm just going to follow this and let's see. As I go from A to D, now I'm going down. That's going to go fast, right? So kinetic energy is going to increase. And then I'm going to hit that low point here, kind of stop for a second. So kinetic energy will actually start to decrease, right? And when that happens, kinetic energy increases, and then it's definitely going to decrease as I'm going higher up. If you've ever been on a roller coaster, you know you go up slow, right? And then I hit another point of higher potential energy. So the correct answer here would be C. This confused a lot of people. Kinetic energy increases, then decreases, And at the same time, potential energy will decrease and then increase. And at which point is kinetic energy of the roller coaster the greatest? That would be right over here, right? Because right as you're hitting the bottom, you're going to be flying and then suddenly stop and then go up slow. So C, as you're getting to that lower point, C is going to be your greatest kinetic energy. All right, and then let's just go one last time to energy sheet 4, and we'll just answer these 5 questions real fast. I put whatever we need from the reference table also next to this sheet. An air temperature of 30 degrees Celsius. 30 degrees Celsius is right here, right? So it wants to know, what is it equal to in Fahrenheit? If I slide over, I don't know if you remember, I said Fahrenheit is the only one that goes up by 2s. So look, 82, 84, 86 degrees Fahrenheit. And that's that answer right there. Which substance has the highest specific heat? Remember what I told you about specific heat? It's the resistance to being heated up or cooled off. And the highest specific heat, if you get a question like this, look, they go in order, don't they? The specific heats. And the highest specific heat is up here, liquid water. Liquid water. Choice B. Number 3, a camper takes a 100-gram piece of basalt rock from a campfire and places in a cup holding 250 milliliters of water. The temperature of the rock is 300 degrees Celsius and the temperature of the water is 20 degrees Celsius. Air temperature also is 20 degrees. Oh my God, this is long. In the process of heating the water with the basalt, the temperature of the basalt decreased more than the temperature that the water increased. Why? Well, look, here's basalt. The specific heat of basalt is 0.84. The specific heat of liquid water is 4.18. The higher the specific heat, the more resistance to changing our temperature. So the explanation for this is water has a higher specific heat than basalt. Number 4, during winter, Lake Ontario is generally warmer than the land areas by it. What's the reason for it? I know I did this the other day, but here you go. Oh, wow. That's not bad. It's not bad for my computer animation. We'll make this an ocean or a lake. It doesn't really matter. It's a body of water. And on a sunny day, ooh, that's not great. Let's make a little sun here. Let's see what I can do with that. Wow, this is not easy. Okay. There's the sun. And if it heats up big time in the summer, the land might go up to 90 degrees. Is the water going to be 90 degrees by the end of the day? No. If the water starts at 70 degrees that day, you know what it's going to end at? Probably 70 degrees. So the reason is water has a higher specific heat than land has. And then over here, number 5, base your answer to the following question on the diagram below. Soil and water are base. Okay, so we're heating up soil. We're heating up water. After the heat lamp is turned off and removed, how will the cooling rates of the soil and water compare? So we heat them both up. They're hot. The basic question here is, what is going to happen? What's going to cool off faster? And remember, we said liquid water has the highest specific heat of anything on Earth. Therefore, it's going to put up a more resistance to lowering its temperature. So the soil will cool down faster because it has a lower specific heat. That is choice B. All right, so that should help you. Those are all the answers to all the questions we did. These are great questions to look at for the quiz tomorrow, and here's what's on the quiz. Just remember, a good absorber is a good radiator. Also, conduction, convection, radiation, this is all the things we did this week. Dark and rough surfaces absorb more energy than light and smooth, which reflect more energy. We just looked at the electromagnetic spectrum on page 14 of the reference table. Know that all heat will flow from high to low energy and high to low temperature. If you ever get the question, what's the main source of energy on Earth? It's the sun. And everything I just went over, temperature and heat and specific heat, know those things. All right, guys, good luck. It's good to actually see you. And that's that. Good luck. Hope everybody's well.